So atomic radius is half the distance between the two nuclei in two adjacent atoms. So when we determine the radius, we can't actually just look at a single atom because remember, there's no well-defined wall of an atom. It's just where we'll see that higher densities of electrons. And so a much better way to measure it is by looking at the nuclei to nuclei distance between two atoms and then taking half of that for the radius. And so this is how we get the radius of these atoms. And we can look at some trends associated with those values. So this picture shows both atomic radius and ionic radius, and we're only going to worry about the atomic radii right now, and those are our pink spheres here that we've got on the screen. And what we want to look at is what's happening as we go from lithium down to neon, from sodium down to argon, from potassium down to krypton. And what we notice is that the atoms are actually getting smaller because we need to think about what's happening as we go from lithium down to neon. And so remember that if we have lithium, it has 3 protons and 3 electrons. If we go to beryllium, now we have 4 protons and 4 electrons. But remember that next electron is not being added to a higher energy shell. It's being added to the same shell, that same energy level as the 3rd electron was added for lithium. And as a result, what we see is an increase in the nuclear charge because now we have +4 in the nucleus instead of +3. But we have more electrons, so we have more attractive force between the protons and electrons. And we don't see any increase in the shielding because that electron is being added to the same energy level. We're not adding electrons between the nucleus and that outermost electron. We're just adding another electron to that same energy level. And as a result, the attractive force increases as we go from lithium to beryllium on over to boron, carbon, nitrogen, and so on. And every time that we go over again, so to boron, we have 5 protons and 5 electrons. Again, we're adding to that same principal energy level, that same in-value shell that we talked about with our orbitals. And so we're just increasing the attractive force between the nucleus and that outermost electron, and there's no additional shielding. And so what happens is the atoms actually get smaller as I go from left to right. The other trend we have to worry about is what happens as we go down the column. So if I look here at lithium, I go to sodium and I go to potassium. And what I see is that as I go from lithium to sodium, now I'm still looking at kind of the same valence configuration, but now I'm adding more electrons to a higher energy level. So the reason it gets bigger is because we're adding electrons in sodium to the n equals 3 shell, whereas lithium only had n equals 2. And as we get higher n values, we're going to see a bigger atom. We'll see the same general trend as we go from neon to argon to krypton, which is not a whole lot bigger, but we will see that same trend happening. So we've got 2 factors at play here. As we go across the row, we see increasing attractive forces between the nucleus and the outermost electron. As we go down the column, we see we're adding electrons to a higher energy level, and as a result, we're going to see bigger atoms. So now we can add something else to our trend here. We've got our increasing effective nuclear charge. Now we're going to add our atomic radius. So it increases as we go down the column, and it increases as we go from right to left. So completely opposite of the effective nuclear charge. And so when we talk about the effective nuclear charge, we said that it was increasing as we went from left to right, and that's a result of that atomic radius. Remember that the atom is getting smaller as we go from elements on the left side to the right side. So we're decreasing the distance between the nucleus and that outermost electron, and as a result, that attractive force is going to be stronger.